Alright students, I gave you 100 multiple choice question midterm review practice gauntlet. I'm going to go over how to solve the problems now. I strongly encourage you to have out your reference table. If you've lost your worksheet or you need a copy, there should be another copy in the link to this video. So in this first question here, you have a book that is falling from some height and then striking the floor. This is an energy problem. What we're saying is all of the potential energy that it has at the top goes into kinetic energy at the bottom because there's no energy loss from non-conservative forces like friction or anything like that. And we're going to take the potential energy at the top and set it equal to the kinetic energy at the bottom. This is a numberless problem. It's just in terms of variables. So the potential energy formula is mgh, at least potential due to gravity. And kinetic energy is 1/2 mv squared. And then what you're going to do is cancel out the masses. You're going to solve 2gh equals v squared. Take the square root of both sides, and that is going to give you v equals the square root of 2gh. If you didn't remember those formulas, it would be a really good idea to have this reference table. Now, for the first semester material, it's almost all on the back page, page 6 of the reference table, with some other facts on the front. So let's look at question 2 now. Scalars and vectors. Scalars have magnitude only, and vectors have magnitude and direction. Speed only has magnitude, so it's a scalar. Velocity is similar to speed, but it also has a direction, so it's going to be a vector. So scalar to vector, this is going to be the answer, but let's just rule out the others. Displacement, change in position, that is a vector, it has direction. Distance is a scalar, it only has magnitude. Displacement is a vector, velocity is a vector, speed is a scalar, and distance is a scalar. So the answer is going to be A. And actually I forgot to put the answer around there. Question 3, when you look at this, this is a car that is accelerating. So if you want to calculate the acceleration, the definition of acceleration is change in velocity over change in time. Put another way, that's final velocity minus initial velocity over final time minus initial time. So let's say we take this row and this row. Final velocity is going to be 8.5 meters per second. The initial velocity is 4 meters per second. The final time is 6 seconds. The initial time is 3 seconds. And that is going to give us 4.5 meters per second over 3 seconds, which is 1.5 meters per second, or meters per second squared. So the answer to question 3 is going to be C. Now for question 4, this is a question about the displacement of an object, or the distance that it travels. Now, a useful skill to know when you're interpreting any graph is the meaning of the slope and the meaning of the area. We do the meaning of the slope a lot. We don't do the meaning of the area as much. If you want to know the area on any graph, if that means something, take the y thing times the x thing and see if that means anything. In this case, the y thing is speed or velocity, and the x thing is time. Well, velocity times time, you may recognize that as distance, because the definition of velocity is displacement over time. Well, displacement is just velocity times time. So the area on this graph of a speed versus time graph is going to tell you the displacement. So we're told to look for the first 3 seconds. So you're going to look from here to here. When you look at this, this area is actually a triangle with a base that's 3 and a height that's 8. Now, you can look at this and you can say, okay, 8 times 3 would be 24. Half of that rectangle, half of this rectangle is going to be 12 rather. Or you can say, well, area of a triangle is 1/2 base times height. Either way, so 3 seconds for the base. The height is 8 meters per second. That's going to give you a displacement that is 12 meters. So the answer there is going to be 12. Looking at question 5, a rock is dropped from a bridge. What you want to do, and what I don't see enough students doing, is what I like to call drawing the big picture. So it's not critical that you draw something fancy. I certainly can't. But we need to label the initial position and the final position. So you're dropping a rock, and we know that initially its velocity is 0 meters per second. You know that it is accelerating as it goes down at minus 9.8 meters per second squared because it's on Earth and the only force acting on it is gravity. We don't know the displacement and we don't know the time in this particular question. It's not asked us to calculate anything, but this is a good time for me to introduce this. So they want to know what happens to the magnitude of the acceleration and the speed. Well, as it falls, this acceleration does not change. This stays the same because the entire time you're falling, the only force acting on the rock is gravity, the weight force. As it falls, it doesn't get any heavier or lighter, so it's going to have the same acceleration, minus 9.8. So the acceleration is going to be the same. Now speed, it is accelerating, so every 1 second that goes by, it's going to be going 9.8 meters per second faster downward. So the speed keeps going up. So we're looking for the speed getting faster and the acceleration staying the same. They don't both increase. They don't both stay the same. The acceleration doesn't increase, and the speed doesn't decrease. The acceleration remains the same, check, and the speed increases, check. So the answer to number 5 is going to be D. Question number 6 is essentially a vector question. Vectors are quantities that have both a magnitude and direction. And when we add them, we can't simply just add numbers like we're used to doing. You need to draw arrows. Now, in this case, you don't have to draw it to scale, but let's draw it anyway. You have a 5 meter per second east, the direction matters that the boat's traveling, so 5 meters per second east. And what I'm doing here is called the head to tail method. I'm going to draw the tail of the second vector at the head of the first vector. And the second vector is going south at 3.3 meters per second. So this is 3.3 meters per second. Now, lucky for us, these two vectors, north and south, are perpendicular. Because they're perpendicular, that means we're going to be able to calculate the resultant without having to actually draw them to scale. The resultant, if you'll remember, goes from the tail of the first vector to the head of the last vector, always. That's going to be the resultant. Now you may remember Pythagorean theorem. The resultant squared is going to equal 5 meters per second squared plus 3.3 meters per second squared. You'll take the square root of both sides. And that should give you a resultant of 6 meters per second. So that was just a Pythagorean theorem. In question 7, we have a baseball that's thrown at an angle, and we want to find what the magnitude of the ball's initial velocity. So this is really a vector question. So what's going on is you throw the ball at some angle, 40 degrees. And you're given the horizontal component of the velocity. So you're told that the x part, this part, is going to be 12 meters per second. We want to know what the resultant is, or what the initial vector was. More often than not, you're given the resultant, the angle, and you have to find the components. This one's actually backwards. I don't think enough students look at the reference table for this one. They forget this is right here. So let's use that. It's always going to be true that the x component of the vector is going to be the magnitude of the vector times the cosine of the direction. So you're going to plug in. You're given the x component is 12 meters per second. We want to find the magnitude of this vector, and you're given that the angle is 40 degrees. Now's a good time for a PSA. Make sure your calculator is in degree mode. For most of your TI type calculators, you'll go to mode, move it to degree. If you're not sure, take the sine of 30 degrees. You should get 0.5. If you're not, it means you're in radian. You're in radian mode. So, oops. The A, when you plug in 12 meters per second cosine 40 divide, is 15.7 meters per second. So the answer there is going to be C. Question 8 is a question that I like to call a numberless question. The equation we're using here is the gravitational force equation. So I'll show it to you on here. Again, I'm trying to encourage you guys to look at your reference table. We're using this formula here. Universal gravity. So Fg equals G m1 m2 over r squared. That's big G, by the way, not little g, not 9.8. And the r here, people always get a little confused, is the distance between the centers of the two objects. So from here to here, it stands for radial distance, but that's going to be r, and this is going to be m1, and this is going to be m2. So we look at the variables that are changing. G is not changing in any of these scenarios. In A, we're going to essentially plug in, I like to make anything that's not changing 1. I'm going to double the mass of both objects. So we're saying, okay, what happens if mass 1 doubles, mass 2 doubles, and everything else stays the same? That's going to make the gravity force quadruple. In the second example, we're looking at just doubling the distance between the objects, everything else stays 1. Well, G and the M's don't change. And then if the distance, that R doubles, remember, that R is squared. So that's 1/2 squared. That's actually going to give you 1/4. So if you double the distance, it's going to quarter the force between the objects. And C, we're going to try doubling both masses. So the first mass doubles, the second mass doubles, and then the distance is also doubled. But remember, that's double squared, so you wind up with 4 on top, 4 on the bottom. That's not going to change it at all. And for 8D, if we double the mass of one object and double the distance, so that's doubling one of the masses, everything else stays the same, and the distance between them doubles, again that's double squared, that is going to give you 1/2. So the only one that makes it gets bigger is the first one. So the answer here is going to be this. Now this particular question didn't ask you to figure out by what factor, but if it had, doubling both masses would increase the force by a factor of 4. It will be 4 times bigger. In question 9 here, they want to know which represents a box in equilibrium. Equilibrium is sort of a magic word. What equilibrium means is that when you take all the forces on the object and you add them all up, the net force is 0. Now for my students, I always tell this story, and it's a little silly, but I like to think about equilibrium when I'm driving. Let's say you're in a car and you are just merging onto the highway. Initially, your engine force is much, much bigger than the drag force. That's why you're accelerating. But as you go faster and faster and faster, and the force increases, the drag force, at some point it's actually as large as your engine force. A lot of people don't believe me when I say that. But the drag force is just as large as your engine force. That's why it takes so much money to pay for the gasoline to keep applying the engine force. At that point, you're in what's known as dynamic equilibrium. Equilibrium because the net force is zero. This force and this force balance out. And the normal force and the weight force. And you're going in a straight line at a constant velocity. So I have this thing I do sometimes where I'm driving down the highway, or my wife's driving, and we merge onto the highway. And right at that moment where we reach a constant velocity, hopefully within the speed limit, there's this moment, this magical moment where you have this Zen state and realize that all of the forces are balanced. All of the forces acting on the car. If you were to take every little tiny force from every molecule hitting your car, they would all add up to zero. And I throw my hands in the air and I say, Eureka, we've done it. We've balanced the forces. Net force is zero. Constant velocity in a straight line. And now that we know energy, we can also say it's a constant kinetic energy. So that's a long-winded way of saying we're looking for the box where the net force is zero. So in this one, the net force is going to be down 5. It can't be this one. In this one, the net force is going to be down 3 because it's 5 down, 2 up. This 2 and this 2 cancel out, so it can't be that one. Now, in this one, the 5 newtons to the right, 5 newtons to the left, they balance. 2 newtons down, 2 newtons up, they balance. This is going to be our answer because the net force is going to be 0. F net equals 0. And, of course, in this one, the net force is going to be up and to the right because 5 newtons is bigger than 3. It's not going to be this one. Question 10 is another gravity one, but it's just a straightforward calculate the gravitational force. So the G, which if you don't remember what it is, you can look on the front page of the reference table. It's right here. And one of the problems I find with students is they don't like to put the units in, I think because they're so long, but at least for a Regents exam, you'll lose 50% of the points on a Part 2 question for that. So you got to be a little careful. So that's 6.63 times 10 to the negative 11 newtons, meters squared over kilograms squared, which granted is a mouthful, times M1 is 7 kilograms and M2 is 7 kilograms, divided by the distance, 2 meters squared. Hold on, I think I have a visitor. I'm back. The tricky part for people sometimes is the squared. You got to remember to square the bottom. It's not such a problem when it's 2, but when it's very small or very large, powers of 10, you got to be a little careful to do that. On your TI calculators, I recommend using the scientific notation. That's the EE button. So you might enter this as 6.63 second and EE, which is the comma button, negative 11 when you put it in. When I plug this into my calculator, I got 8.12 times 10 to the negative 10 newtons. When I look at the choices, that is going to be closest to C. For 11, you have an object that is thrown horizontally and one that is thrown, or dropped rather, vertically. In both cases, they're actually going to hit the ground at the same time. The reason is the vertical direction and the horizontal direction are completely independent of one another. In my classes, I like to talk about this as if the X is in red and the Y is in blue and never making purple. Yes, the horizontal one has a very fast horizontal velocity, but it doesn't have any vertical velocity, and the one you dropped doesn't have any vertical velocity initially. Excuse me. So, because they're horizontally launched, the initial velocity, the VIY equals 0 for this, and the VIY equals 0 for that. So they will always have the same vertical velocity at all times. Because of that, they will always have the same height. Now, they'll have different momentums, kinetic energies, because they'll always have different velocities, because the one on the right here does have a horizontal velocity. But they will always have the same height because they'll always have the same vertical velocity. Number 12 is just a straightforward direction. In centripetal motion, what's going on is the object would go in a straight line. It would go in the direction of its velocity, its tangential velocity, velocity at tangent. If I was to cut this chord, it would go this way. But there's a force pulling it towards the center. So there's a centripetal force towards the center, and the acceleration is towards the center. Even though it's not speeding up or slowing down, it is accelerating because it's changing direction. So that's going to be choice A here. Okay, 13 is a question that highlights the difference between velocity and speed. Velocity is truly displacement over time. Displacement has a direction. So when you're figuring out the displacement for the first car, it's going to be 40 meters east. That east matters in 5 seconds, which is going to give us 8 meters per second east. The second vehicle travels 64 meters, but that's west in 8 seconds. And that gives you 8 as well, but that's 8 meters per second west. So here's a case where both cars have the same speed, but they have different velocities because they're traveling in the same time rather, or at the same speed. So during their periods of travel, which were different, the cars definitely had the same speed or average speed. Their momentum, displacement, and velocity were all different because they're traveling in different directions. This next question, question 14, is another question about displacement. If you remember from earlier, the area on any graph is equal to the y thing times the x thing. In this case, that's velocity times time, which gives us displacement. So we want to know when the cart arrives back to its starting point. Another way of saying that is when the area above the graph here is balanced out by an area underneath. So we turn this into a triangle, and this triangle, 20 by 3, would be 60, but a triangle cuts it in half, so that's a displacement of plus 30 meters from there. Here it's only 2 seconds across by 20, which would give you 40, which would give you this plus 20 meters. Now we have to see on this other portion of the graph, when does that displacement essentially equal to minus 50? We have another triangle here that's the same size, 2 seconds by 20, but negative. That is going to be negative 20 meters. So then the question is, how many seconds have to go by until this area is equal to minus 30? So this is 20 seconds. So displacement is velocity times time. We need this to be minus 30. And the speed is minus 20 meters per second. What's the time? So we need to travel another 1.5 seconds to make that happen. So another 1.5 seconds takes you to there, which will give us the remainder of minus 30 meters. And that takes us to 8.5 seconds. So the answer for the total time is 8.5 seconds until the displacement finally adds back up to 0. In which direction is the car traveling at 4 seconds? At 4 seconds here. Now, a lot of people are drawn to the slope because we frequently do slopes and interpret them, but the slope on a VT graph is the change in velocity over time or the acceleration. It's not a negative velocity. It's not moving to the right. Because the velocity is positive, you're going to be traveling to the positive direction. So your displacement will be positive. Now what's interesting about this graph is we're used to positive being right or up in this case because it tells you that it initially starts moving northward. The positive displacement means to the north. So the answer here is going to be to the north. 16 is a question about a projectile. They want to know what's the direction of the acceleration. The acceleration the entire time is down with an acceleration that is equal to g, negative 9.8 meters per second squared. The force doesn't change the entire flight. It's always pointed down. So the acceleration at point D and everywhere else along the flight is going to be pointed down. Let's see, question 17. The key word here is horizontal acceleration. Vertically, the acceleration is constantly minus 9.8, but horizontally, the acceleration in the x direction is 0, always, because there's no force pushing it sideways. There's only gravity pulling it down. So the acceleration is strictly down. It's not horizontal at all. In question 18, you're given an object and an acceleration and a mass. This is an F net equals ma question. So you're told it's 4 kilograms, and the first time you push it, 3 meters per second squared. And the second time you push it, it has the same force, but it has half the mass. Now there's two ways of doing this. You could actually do the calculations, or you could just sort of reason it. Let's just sort of reason it. Acceleration equals F net over m. When you look at the mass here, when you go from 4 kilograms to 2 kilograms, your mass is halving. Net force stays the same. The mass halves. That's going to give you an acceleration that doubles. That's 2 times. Now this question gave you numbers, so you actually could do it. The first time through, you're going to have an F net that's equal to ma. That's going to be 4 kilograms times 3 meters per second squared. The force is equal to 12 newtons. Well, on that second object, if you want to know the acceleration, F net over m, that's going to be an F net of 12 newtons over a mass that's now only 2 kilograms. That's going to give you an acceleration of 6 meters per second squared, which, as you'll notice, is half, or rather twice, of the acceleration before. So the answer is going to be 6. 19 is a question I like, comes up a lot. Again, you'll want to draw the big picture. So basketball player jumps up in the air, grabs a rebound, and comes down. Picture really helps here. We know that the velocity at the top here is 0 meters per second. We also know, because this is on Earth, that the acceleration is minus 9.8 meters per second squared, and we're told that the total time, the time to go up and come down, is 0.8 seconds. What I like to do is I like to make the top the initial position, which means the time just to go up here, or down rather, is going to be half that, 0.4 seconds. At this point, we need to look at the reference table and look at our constant acceleration formulas. We're looking for a formula that has d, the thing we want to know, and we know everything else. So when you look at the formulas here, the first few, the equation that fits the bill has a d, we know vi, we know t, we know a. We can use this formula. That's the one we're going to use. Here, d equals vit plus 1/2 a t squared. Vi is going to be 0. D is what we want to know. The acceleration is minus 9.8 meters per second squared, and the time we're using, because we're only going from the top to the bottom for the purpose of this calculation, is going to be the half time, 0.4 seconds, and you square it. When you do that, you're going to get a displacement that is minus 0.78 meters. That just means from the top to the bottom you went down 0.78 meters. So the highest point you reached was 0.78 meters. And 20 is a question, do you understand period? Period, by definition, is the time it takes for a pattern to repeat. In this case, for an object to go around in a circle once, that would be the period. So period, or t, equals time for one revolution, or the time 8 hours over 4 revolutions is going to give you 2 hours per revolution, or 2 hours for the period. So that's question 1 to 20. A little long-winded, but that's why I have a fast forward button.